What you're looking at is a 30-year US Treasury bond, a loan to the US government, considered one of the safest investments on Earth. But something strange happens to this safe bond when interest rates start to move. Imagine you bought it today for $91.86. Over the next year, rates rise by 3%. Your bond loses 36% of its value, $360 on every $1,000. Not a great showing for the safest investment on Earth. Now imagine that same bond, same 3% move, only the other direction. If the math were a perfect mirror, the gain should match the loss exactly. Watch. Your bond gains 74%. Not 36 in the other direction, 74. More than double the loss. Same bond, same size move. Two outcomes that don't mirror each other at all. The mirror is broken, and we're here to find out why. This isn't a quirk. It's true of every bond, every mortgage, every pension liability. In every one of them, the mirror breaks in the same direction. It has a name. It's called convexity. In a few minutes, you'll know what it is, and why it always tilts the math in your favor. So why does this happen? Why should the same size rate move in two opposite directions produce two outcomes that look nothing like mirror images of each other? To see why, we need to build the picture from scratch. On the left of the screen, we're going to lay out every cash payment our 30-year Treasury makes over its life. One rung of a ladder per year, with each rung's height representing what that single payment is worth today, given today's yield of 4.5%. You're looking at 30 rungs in total. 29 of them are the small annual coupon payments, and the very last one carries the principal back along with the final coupon, which is why year 30's rung dwarfs all the others. Stack the rungs end to end, and you get the bond's price. For our 30-year Treasury at 4.5% yield, the rungs add up to $91.86, which we then plot as a single dot on the chart over to the right. At the bottom of the screen sits a dial labelled Yield, currently set at 4.5%. Yield, very simply, is the interest rate the bond effectively pays you, given whatever price you bought it at, and the dial is going to be the engine of everything that happens next. Watch what happens when I turn the knob up by a hair, when yields rise just slightly, from 4.5 toward 5. Every rung of the ladder shrinks, but not equally. Year 1's rung shrinks barely a hair, while year 30's rung shrinks noticeably. The further out in time the cash flow is, the harder it shrinks under the higher yield, and that uneven shrinkage is the secret of the entire video. The reason faraway cash flows shrink harder than nearby ones is simply that discounting compounds with every passing year. At a 5% yield, a payment 1 year away gets divided by 1.05 just once, while a payment 30 years away gets divided by 1.05 30 times over, and the multiplied effect on the far-out rung is enormous. As the rungs shrink, the total ladder height drops, and a fresh dot lands on the chart over to the right, at the new yield with the new total price. Now I'm going to keep turning the knob through 5, 6, 7% and beyond. At each new yield, the rungs resize, the total height adjusts, and a new dot deposits onto the chart. Watch the dots leave a trail behind them. And now turn the knob the other direction, back through 4.5, down to 3, then 2, then 1. This time the rungs grow rather than shrink, the total ladder gets taller, and the dots deposit themselves to the left of where we started. Run the knob across the full range every yield this bond could face, from near zero all the way out to 15%, and the dots leave behind a continuous trail. That trail, every dot the knob ever made, is the bond's price-yield curve. It is not a line. It bends. The slope of that curve, right at today's yield of 4.5%, is called modified duration, 16.69 for the 30-year. It's the curve's local steepness, measured exactly at the spot where we're standing right now. If you extend that tangent line outward in both directions, pretending, just for the sake of argument, that the curve really were a straight line. Duration alone says a 1% rate rise costs you about 17% of price. A 2% rise costs you about 33, and a 3% rise costs you roughly 50. But those are the line's predictions, not the curve's. And the line and the curve only agree at exactly one point, the spot where we drew the tangent, 4.5%. Everywhere else along the chart, the line is wrong. And look at how it's wrong, because this is where the asymmetry between rate up and rate down outcomes starts to make sense. To the right of where we started, meaning rates went up, the actual price in solid gold sits above the dashed line every time, which is to say, the bond didn't lose as much as duration alone would have predicted. To the left, where rates went down, the curve again sits above the line, but this time it means the bond gained more than duration predicted. This is what the asymmetry looks like in geometry rather than in dollars. The curve always sits above the line, on both sides of where we started, always in the bondholder's favour. That gap between the line and the curve has a name, and it's the whole video. But before we name it, we need to feel it, on the seesaw. Bonds can be modelled as a seesaw, a flat plank balanced on a fulcrum, with each future cash payment from the bond sitting on the plank as a weight, placed at the year it's scheduled to be paid. When yields rose, we pressed down on the seesaw and the plank tilted in response, with the angle of the tilt corresponding to the size of the bond's price drop. That tilt, that linear, predictable tilt, was duration. But to make the math clean last time, we treated the weights as if they stayed exactly the same size when the seesaw was pressed. That was an approximation, and now we have to lift it. When yields rise, every single cash flow's present value falls, and the further out in time the cash flow is, the harder it falls, because compounding amplifies the discount with every passing year. So what happens to the seesaw when we press it now, with the weights free to change size as the yield changes? Watch carefully. Two things happen at the same time. First, the plank tilts under the press, the way it always did. That's the duration response. But second, each weight on the plank visibly shrinks. The year 1 weight barely budges, while the year 30 weight loses noticeable mass. And because the weights have shrunk by uneven amounts along the plank's length, the plank doesn't stay straight under the press. It bends. The far end, where the heavy year 30 weight has just gotten lighter, rises a little above where a perfectly rigid plank would have sat. The flex is the geometry's way of saying, the math just changed underneath the plank. That flex, the part of the seesaw's motion that duration could never see, because duration assumed the weights were frozen, has a name. It's called convexity. And here's the gift hiding inside the geometry. The flex always lifts the plank upward, regardless of which direction we press from. When rates rise, a move that works against the bondholder, the weights shrink unevenly, the plank flexes upward, which lifts the cash flows above where the rigid prediction said they'd land, meaning the loss ends up smaller than duration's number suggested it should be. And when rates fall, a move that works for the bondholder, the weights grow unevenly, but the plank still flexes in exactly the same direction, upward. So the gain ends up larger than duration's number suggested it should be. Either way the rates move, the plank bends in favour of the holder. The flex doesn't care which direction the press came from, because the uneven shrinkage of the weights doesn't care either. The plank bends because the weights themselves change, and the holder of the bond always ends up winning by a little more than they could ever lose. Now let's make all of this precise and actually compute it. Here's the bond's price yield curve again. Suppose rates change by some amount, and we want to predict where the new price lands. We have 3 increasingly accurate ways to do that, and we're going to draw all 3 of them, stacked on top of each other, right on the chart. Layer 1. Assume the price doesn't move at all. a flat horizontal line at today's price. Obviously wrong, but it sets the baseline we're going to build on top of. Layer 2. Use the slope of the curve at today's yield. A dashed line, tilted, accurate at exactly one point, the point where the line touches the curve. That's duration. We've already met it. Layer 3. Start with the duration line and add an upward correction shaped like a parabola. That correction is convexity. It's the new piece we're after. And here's the magic. If you take the duration line and add the parabolic skirt to it, point by point along the chart, the sum traces the actual price-yield curve, right on top of it. So the actual curve really is just two simpler shapes stacked together, a straight line plus a parabolic skirt. Written in one equation, the third option says, the percent change in price is approximately equal to minus duration times the rate change, plus 1/2 times convexity times the rate change squared. All of that is just a fancier way of saying the same thing twice. For a small rate move, use the slope on its own, and for bigger rate moves, add a correction that accounts for the fact that the curve is bending. Now look closely at that second piece. The rate change is squared, and squaring is older than algebra. Long before anyone wrote a formula, squaring a number meant something physical, drawing a literal square with the number as its side length and reading off the area. So slide the rate change from positive 3% through 0 down to negative 3% and watch the square get drawn beneath the number line. When the rate change is plus 3, the square has area 9. When the rate change is minus 3, the square hangs on the other side of 0, but it has the same area, 9. The square doesn't care which side of 0 its side length came from. Area is just area, and it can never go negative. Which means convexity always adds to your return, whether rates rise or whether rates fall. Always. For the same reason a square always has positive area, no matter which side of 0 you measured its side from. So now let's actually compute convexity for 3 US Treasury bonds, the 2-year, the 10-year, and the 30-year. Starting with the 2-year, modified duration of 1.88 and a convexity of 5.35. The 10-year, modified duration of 8.04 and a convexity of 79.52. And then the 30-year, modified duration of 16.69 and a convexity of 398.41. These convexity numbers look enormous compared to the duration numbers, and they are. The 30-year has nearly 75 times the convexity of the 2-year, while only having about 9 times the duration. Convexity grows much faster with maturity than duration does, and we'll come back to why that matters in a moment. But before we put any of these numbers into the formula, we should pause and ask what they actually mean. What's 398 measuring, and how is it different from what 16.69 is measuring? Because these are two genuinely different kinds of numbers, and feeling that difference is what makes the formula click. Modified duration is the slope of the price-yield curve at today's yield, the steepness of the dashed line we drew through it. For our 30-year, that slope is 16.69, a single number that tells you how fast the curve falls, right at 4.5%. Convexity, by contrast, is something genuinely different. It's the height of the parabolic skirt we just drew on top of the line. Or, equivalently, it's the number that says how fast the slope itself is changing as yield moves. If the bond's price-yield relationship were a perfectly straight line, the slope wouldn't change at all, and the bond's convexity would be exactly 0. But the relationship is a curve, not a line, and convexity is the number that captures how much the curve bends away from any tangent we draw on it. On the seesaw, the picture is even cleaner. Modified duration tells you where the cash flow weights balance, on average, the location of the fulcrum. Convexity tells you how spread out the weights are around that balance point. The first quantity is a single average, the second is the variance around it, and we'll see in the next scene exactly why that distinction matters. So what does a convexity of 398 actually do for you, in real percentage points of return? The convexity term in the formula is 1/2 times convexity times the rate change squared. So let's plug in different rate moves and watch how much convexity gives back at each one. For a 1% rate move, convexity adds back roughly 2 percentage points to your bond's return, a useful but modest contribution. For a 2% rate move, convexity adds back about 8 percentage points instead, suddenly a much more serious correction. And for a 3% rate move, convexity adds back almost 18 points on top of whatever duration alone would have said. Notice the pattern in those three numbers. When the rate move doubles, convexity's contribution actually quadruples, and the reason is right there in the formula. The rate change is squared, which means convexity matters disproportionately more the bigger the rate move gets. And now we can finally see why the number's 75 times larger comparison from earlier matters. The 2-year has a convexity of 5. The 30-year has nearly 400. And that gap is precisely why long bonds are so much more sensitive to big rate moves than short ones. Not because they have more slope, but because they have so much more curvature beneath it. Now let's stress test the formula by pushing it past where it's meant to work. Take the same 30-year Treasury and a brutal 7% rate rise. Watch the cursor walk along the dashed line, the duration prediction. At plus 1%, the line says minus 17. At plus 3%, the line says minus 50. At plus 5%, the line says minus 83. And then, at plus 7%, the cursor crosses the $0 floor, and the line says the bond has lost 117% of its value, which is of course impossible. A bond can lose up to 100% of its value, the entire investment, every cent of it, but it cannot, by any mechanism, go below zero. The dashed line crashed straight through the floor because the formula has no way of knowing that the floor exists. Now walk the cursor back along the actual gold curve all the way to plus 7%. The curve doesn't crash through the floor, it bends. It approaches zero from above and never crosses, because real bond prices are anchored by reality, not by a straight line approximation. So what happens when we add convexity to the rescue? Plug it into the second term, 1/2 times 398 times 7 squared, divided by 100 to put it in percentage units. Convexity adds back 98 percentage points to duration's prediction. Together, duration plus convexity now says the loss should be about minus 19%, which is at least a number that lives in reality, rather than the impossible minus 117 we started with. But the actual price of the bond, computed directly from its remaining cash flows at the new yield, turns out to be down by about 59%. So the formula was perfectly honest in pointing out that minus 117 was wrong, but it wasn't quite honest enough to land on the right answer either. The reason is that convexity is only the second term in a longer mathematical correction series, and there are smaller, finer correction terms after it. For typical rate moves of 1%, 2%, or 3%, duration plus convexity is an excellent description of what happens. But for 7% rate shocks like this one, the formula simply isn't enough on its own, and you have to compute the price directly from the cash flows. The point of all this isn't that the formula is exact in every regime. The point is something simpler than that. Convexity is the next, biggest, and most important correction to duration that exists. And unlike most corrections in finance, it's always working in the bondholder's favor. We've seen why the plank flexes, because the cash flow weights themselves change size under a press. Now we need to ask what makes some bonds flex more than others. Watch this. 2 seesaws side by side. Both have the same fulcrum position, meaning both bonds have exactly the same modified duration. But the bond on the left has all its weight concentrated at one point, right at the fulcrum. The bond on the right has its weight spread out along the plank, balancing at the same point, but distributed over years. Now press both seesaws with the same rate move at the same time. Both planks tilt the same first-order angle. They have to, because they have the same duration. But look at the right seesaw. Its plank flexes much more than the left one's does, and the difference is the spread of the weights. What we just discovered has a name in physics. It's called the moment of inertia, and what it measures is exactly this: how spread out a system's mass is around its balance point. Spread the mass farther out, and the system has more rotational inertia about its center. In bond mathematics, the same idea has a different name. We call it convexity. Modified duration is the first moment of cash flows. It tells you where the weights balance on average. Convexity is the second moment of cash flows around that balance. It tells you how spread out they are. Same physics, different vocabulary. Now let's run 3 real cases through this lens. The first case is 2008, the year of the global financial crisis. To stop the panic spreading through the financial system, the Federal Reserve cut interest rates aggressively that year, taking them from 5.25% down towards zero in a matter of months. Long Treasury yields followed the Fed down, falling by roughly 1.5 percentage points over the course of the year. Take our 30-year bond and drop its yield from 4.5% down to 3%. Duration alone, the first moment, the slope at today's yield, predicts a price gain of about 25%. What does the second moment add on top? Roughly 4.5 more percentage points, coming from the spread of the cash flows around the fulcrum. And reality that year landed near plus 30%, which is duration's 25 plus convexity's 4.5, almost exactly equal to the actual return that bondholders received. In a year when nearly every other major asset class was crashing, long treasuries quietly gained about 30%, and most of the why, the part that duration alone couldn't account for, was the second moment of cash flows working in the holder's favor. Now run the same exercise the other direction with 1994. The Federal Reserve surprised markets that year by hiking rates 7 separate times, taking funds rates from 3% up to 6% in less than 12 months. Long bond yields followed them up, rising by about 1.5 percentage points, and the bond market had what came to be called the bond massacre. Take the same 30-year and lift its yield from 4.5 up to 6. Duration alone, same slope, same first moment, now predicts a price loss of roughly 25%. What does the second moment add this time? The same 4.5 percentage points it added in 2008, because the second moment doesn't care which direction the press came from. So the formula now predicts a loss of about 20.5%. Reality landed at minus 21. Convexity took 4.5 points off the loss, compared to what duration alone said it would be. On a $100 million bond portfolio, that's $4.5 million saved by something duration alone, the slope alone, could not see. One last case, because it's where the second moment reaches its most extreme form. Most bonds pay you small interest payments every year, coupons, and then return your original principal back at the very end, when the bond matures. But there's a special class of bond that doesn't pay any coupons at all. All of the cash arrives at the end, in one single payment, 30 years from today. These are called zero-coupon bonds. On the seesaw, a zero-coupon bond puts every single weight at the very far end of the plank, at year 30. You might guess this means the spread-out coupon bond would have more convexity, since its weights are more spread. But that's not how the second moment works. Convexity rewards squared distance from the fulcrum, not the breadth of the spread itself, and a single weight parked at the maximum maturity, sitting far past the balance point, generates more second moment than any spread of coupon weights ever could. Our 4% 30-year had a modified duration of 16.69 and a convexity of 398. A zero-coupon 30-year, same maturity, no intermediate coupons, has a modified duration of 28.71 and a convexity of 851. More than double the second moment of the regular coupon bond. Zero-coupon bonds are how big institutions buy convexity in its purest, most concentrated form, which is also why a long-dated zero-coupon bond is one of the most volatile assets that exist anywhere in financial markets. When a hedge fund wants to bet not on which direction rates will go, but simply on the fact that they'll move at all in some direction, they often reach for long-dated zero-coupon bonds, because the second moment of cash flows profits in either direction the rates take. The bigger the move, in whichever direction it lands, the bigger the gift. So let's pull all of this together and lock in what we've actually seen. A bond gains 74% when rates fall by 3, but only loses 36 when rates rise. The mirror is broken, and now we know exactly why. The relationship between bond prices and yields is curved, not straight. The straight line that duration draws sits below the curve on both sides. So whichever direction rates move, the actual price ends up higher than the line predicted. Bigger gains, smaller losses, every single time. The flex of the seesaw says it the same way. The plank bends because the cash flow weights themselves change size under a press, and the spread of the cash flows around the balance point, the second moment in physics terms, is what determines how much the plank bends. All of that has a name: convexity. And here's the part most people miss. Convexity isn't really about bonds. It's about curves. Any curve. Anywhere in finance, or anywhere outside of it, where the relationship between two things bends rather than going in a straight line. Watch the grid. Bond price versus yield on the top left, the curve we've been studying. An option's price versus the price of its underlying, top center, a curve traders call gamma. A mortgage's prepayment rate versus interest rates, top right, the famous exception, where the curve actually points the wrong way. A swaption price versus rates, bottom left. The braking distance of a car versus its speed, bottom center. A drug's effect versus its dose, bottom right. On every one of these curves, bonds, options, mortgages, brakes, drug responses, you can pick a point and draw a tangent line. And in every case, the curve sits a little above or a little below that line. The gap between the line and the curve is convexity. It is the universal name for the price you pay for pretending a curve is a line. Most of the curves you'll meet in finance bend in the bondholder's favor. The gap shades above the line, meaning the curve's reality is better than the line's prediction. Mortgages are the famous exception. When rates fall, homeowners refinance and the cash flows shorten on the lender. The gap shades below the line instead of above. Convexity exists, but it points the wrong way for the holder. And that's a story for another video. Two numbers do almost all of the work. Duration tells you the slope of the line, and convexity tells you how much the line is actually a curve. Together, those two numbers describe almost everything about how rate changes ripple through the entire financial system. And once you can see the bend, you start seeing it everywhere.